Ah, okay. Technology. I see. Okay, so hello everyone. Thank you for coming. I'm going to be giving these lectures today and then on Monday in the W star topic. And my presentations, at least today, will be on the predual with Neumann algebra. And I guess we'll see. We'll see how quickly this goes. I'm very closely following the goals notes, and I put in mostly at the end some remarks that I think are sort of useful to make when one is teaching about this. But let's just get started and then see where we go. Um, so I guess this is all rehashing stuff that you may be familiar with, but I figured that in order to situate ourselves in the topic of this lecture, that I should recall some particulars about dual spaces. So much of the things about dual spaces that you know it works for norm vector spaces in general, but for us it will be enough to think about Banach spaces, which is going to be the main sort of object that we're going to study today. Um, so if I have a norm vector space or a Banach space, the dual space, the space of all linear functionals, um, I should say continuous linear functionals, is automatically a Banach space with the sort of operator norm on the linear functionals. And so there's automatically two natural topologies to think about when you're looking at dual spaces. There is this norm topology, but there's also the much more flexible weak star topology, which is the topology of pointwise convergence on these linear functionals. So in terms of analysis, why are these spaces useful? I mean, in the functional analysis classes you may have taken, you've definitely seen duality arguments. You've seen, LP, LQ, or the Holder exponent type theory. And of course, in goals, I mean, we talk about sort of linear functionals on Banach space as well, I guess, on C-star algebras and stuff all the time. And this is where the example is. So this is, for example, why you should care about dual spaces. So if you have a C-star algebra, which is in particular a Banach space, I guess, the norm unit ball. So here, this subscript one refers to the space of all of those linear functionals with norm, as in this definition above, less than or equal to one. For instance, contains the states, right? On X in your C-star algebra. And for analysis, why is this nice? Well, because in this natural weak star topology, this unit ball is actually compact. This is the Banach-Alaoglu theorem that you may have seen in functional analysis. Um, Now, this is nice. Compactness is a nice thing to have in analysis, but it's not necessarily so tractable because if your original space X is separable, then this weak star topology turns out to be a topology which is metrizable on bounded subsets um, of the dual space. Then you get this sequential compactness. Right. So what I mean, right, is that if you have a compact space from analysis, you're really used to saying, okay, I have a compact space. That means every sequence has a convergent subsequence or something like this. Such a thing is not necessarily true. It's true in metric spaces, right? And that's where the separability on X is a nice assumption. Separability in what topology? So for X, the separability I mean to be in the norm topology as a norm vector space. Um, so Right. I'm saying this is a sort of setup also for my Monday lecture, which is going to be the Kaplansky density theorem, but I don't expect you to remember so much all through the weekend. But the point is that this issue of sequential versus non-sequential compactness, I will sort of use it to motivate some of the reasons why you should care about Kaplansky density. Um, and just I should say, just as a sanity check, is that often if you're talking about X being like your favorite von Neumann algebra, say L infinity of the unit interval, it's not going to be separable in the norm topology. So the dual space of something like L infinity or something like B of H is a huge space, and it's quite intractable. And you see that you might have, for instance, compactness, but you're not going to necessarily have sequential compactness. Um, Okay, I should say I'm not quite sure what the etiquette is, but I assume that questions are sort of okay to just sort of shout out or write in chat or whatever your preference is. But unless that's made explicit, I will make it explicit. If you have a question or you see something wrong, just yell at me and I will seek to correct it. So yesterday, Yoon gave you a lecture about the sigma topologies, if I'm not mistaken. So I just wanted to recall that briefly here. So remember that the sigma weak operator topology for a von Neumann algebra is defined in this way. Let's say I'm going to use this. Well, this wasn't really how you defined it, but this was the sort of one of the theorems that you saw at the end of the lecture. And so the two key things here is that the sigma weak topology is sort of like a slight weakening of the weak operator topology. Um, Weakening, strengthening, I guess. Okay, so instead of looking at finite rank operators, convergence against with respect to the trace against finite rank operators, you have these trace class operators, so L1. Um, and the point was that the bounded operators on your Hilbert space on which you're representing your von Neumann algebra is going to be isomorphic as a Banach space, so the dual of the trace class operators via this duality, right? So if I have an operator on the Hilbert space, so I have x and b of h, then that automatically defines a linear function on L1 by just taking the trace against that operator. And this duality precisely gives you the sigma weak topology. The weak star topology will be the same as the sigma weak topology. Okay, so rather than having a sort of asymmetric thing where I say, okay, B of H is a dual of L1, which is true, I will just call these things dual pairings for the following reason. Um, and this will be important in some of the arguments that I'll give later on, which is to say that if I have an element of B of H and an element of L1, they each can define linear functionals on the other, right? So they both play roles as the arguments of linear functionals, but also as linear functionals themselves. So if I have X and B of H, as I said before, that defines you a linear functional on L1. However, if you have something in L1 that can also be used to define a linear functional on B of H, we get the same exact formula, right? And so this is why we refer to this thing as a dual pairing. Okay, so I guess in Von algebra, at this stage of developing the theory, what you want to do is you want to check some phenomenon happens for B of H and also for the commutative case, and then you say, okay, well, it happens for all the other ones, which is what I'm going to do. But at least this example that I'm showing next is meant to set up some of the theorems. So here's a commutative example. So I am using L infinity, the unit interval, for simplicity, but I don't need the specifics of the unit interval. Like I think there's some other, your typical sort of infinite dimensional abelian von Neumann algebra will also work. So there's this classical dual pairing between L infinity and L1 of the unit interval, right, which looks very similar. So if I have a function in L infinity, this is my little f, right, that defines a linear functional on L1. And here I would like for you to think of this f dx as a measure itself, okay? Maybe it's not a positive or a probability or something, but, measure. And similarly for a function that's in L1, right? L1 of the unit interval will also define linear functional on L infinity by the same exact recipe. Now, what about those normal linear functionals on L infinity? And for this, I'm not going to give a complete treatment, but I'm going to sort of give an example which spells out what I said above a little bit more detail, which is the following. So suppose that I look at L infinity of 0, 1 as a von Neumann algebra. So I'm thinking of it as a subalgebra of bounded operators on L2 of the unit interval. Um, And so I'm going to take a linear functional on L infinity, which I suppose, works as a linear functional on all of B of H, but I'm choosing to think of it as a linear functional on L infinity, which is just going to be a sort of vector linear functional, right? So it's just going to be given as basically by an inner product against some vector, some pair of vectors. Um, okay, so this is clearly a weak operator topology continuous functional. It's definitely normal. For normal, you probably want these square summable sequences, right? And so I'll leave you to generalize the example that I'm giving right now to sort of normal linear functionals where they're not given by a single vector, but maybe by these sequences. But let's just focus on this for simplicity. So what does this phi look like? Well, I mean, if I apply it to some element of L infinity, then I can write down an explicit formula for what phi of f is, as I did right here. And I rewrote it in this suggestive notation as the integral of f against some measure. So I think of this normal linear functional as giving me some kind of a measure on 0, 1. And if I have two L2 functions, of course, I take their product. That's going to be in L1. That's a Cauchy-Schwarz, right? Um, and in particular, this measure over here, this mu, is absolutely continuous with respect to the Lebesgue measure on the interval. And so I'm roughly just sketching out this correspondence for L infinity. I have normal linear functionals. And I can think of this as being in sort of correspondence. Okay, I gave you a very shady justification for one direction of this correspondence, but you can think of this and you can try to fill in the gaps here. That's in correspondence with these integrable functions on L1. And then your classical Radon-Nikodym theorem tells you that those can be put into correspondence with measures which are absolutely continuous with respect to the Lebesgue measure on the interval. So in this case, you can see that there's also this duality of L infinity and L1, and it fits nicely in the normal linear functionals, which play a role in this duality, fit nicely into the duality picture, right? So um, rather, I guess what I mean is that if I have a normal linear functional, I can think of it as an element of L1 in the commutative case as well. Okay, so like I said, we have two examples. So now I guess we try to make it true for the general case. So if I have a Neumann algebra, I'm going to denote by this m lower star the set of normal linear functionals. Sorry, I have some difficulty pronouncing linear today, but I'll do my best. So normal linear functionals from m to c, and this is what we call the predual. The of being in bold text is not, that's an accident. It's predual, not predual of. Um, right. So this is going to be our object of interest, and so we'll see where this goes by the end of the slide. Why was it called a pre-dual? Well, okay, so the first slide we kind of saw that trying to find the dual of a Neumann algebra, okay, may be a little bit difficult, especially because, you know, the separability issues, it may not be sort of worthwhile. But the previous two examples, the theorem with B of H and L infinity, hopefully gives some motivation as to why looking at the subspace of the normal linear functionals might be interesting. And so that's where we'll find a place for M in this duality picture. So if I have an element of M, it will give me a linear functional defined on the normal linear functionals, right? This is what I denote by this x hat. So each element of M acts on a linear functional just by evaluation. And this is something that you've seen, no doubt, many times at this point. So for instance, Galfond duality, right? Um, and so indeed, I have a dual pairing, as I referred to it before, right? So each x defines a linear functional on this predual, and each element of the predual, by definition, defines a linear functional on M. And so what you have here is this sort of identification of M, the von Neumann algebra, as a subset of the dual space of the predual, right? This subset sign is sort of mildly false, right? Because what I'm saying is that the linear functional that I'm defining by the element M is what is like, right? So it's not this containment here is meant to be sort of in spirit. You know? And in fact, the point of the lecture today is to show that in fact every linear functional on M star M lower star on this predual is given by such an x hat. And that the sigma weak operator topology, this normal topology, is the weak star topology in this duality. So a von Neumann algebra will have a predual, which is going to be, in particular, a Banach space. M is going to be the dual space of this Banach space. And the sigma weak operator topology, which you were introduced to last lecture, which may seem to be maybe a little bit ad hoc, has a very natural role to play as the weak star topology in this duality. Okay. And so you see, I guess we get some sort of benefit out of putting M not as like not trying to find the dual of M necessarily all of the dual of M, but thinking of M as the dual space. Okay. Um, so any questions so far? Okay. If not, I will continue. Okay, so first, let's understand what this pre-dual M lower star is. So of course, if I have a sigma weak operator topology can okay, so I guess let me say first that I'm thinking now of having my Hilbert space H fixed. My von Neumann algebra M is a subalgebra of B of H, satisfying the usual axioms. If I have a sigma weakly continuous functional on B of H, then the restriction onto M, which is just a subspace, is going to be sigma weakly continuous, no problem. However, I want to see if I have sigma weakly continuous functionals which are defined on M a priori, can they be extended to linear functionals on B of H that are still sigma weakly continuous, right? Because if I can't do this, then I have no real hope of concretely describing what a sigma weakly continuous functional looks like in the abstract, right? In concrete examples, and maybe able to write it down, but maybe not in general. And that's what this lemma helps us achieve. So this is 3.3.2 in the goals notes. So, which is precisely gives you what tells you that you can do what I say you want to do. So if I have a subspace of B of H and a sigma weakly continuous linear functional, I can extend it to a sigma weakly continuous linear functional on all of B of H. And this proof I will omit. This is a Hahn-Banach type proof, but actually it's very similar to how you prove the statement that, or I guess how you prove the general formula, or how you describe the general formula for, let's say, weak operator topology continuous functionals on B of H, right? So if you like, you can go and inspect that proof. It's actually very um, similar. Um, Now, what's nice about this lemma though, right, is that if I have a sigma weakly continuous functional on M, I can extend it to one on B of H, and I know what those look like, right? So this was the first theorem that I flashed on the slides, but it's also probably the sort of punchline of the last lecture, right? Which is that if I have a sigma weakly continuous functional, it's given by trace against some trace class operator, right? And so this tells you that actually it's very concrete what M lower star is, what this pre-dual is. It is literally all of those linear functionals of the form trace against some trace class operator, restricted to M. Right? So this gives you a very concrete description, and it tells you that in fact there is a surjection from trace class operators to the pre-dual, where I take a trace class operator and I look at the linear functional that's given by it and I restrict it to M. So this will get us closer to understanding what this pre-dual actually is um, by linear algebra, basically, right? So if you think about L1 and M lower star as sort of vector spaces, forget about norms for a second, right? You have a surjection from one vector space to another. So you can use your rank nullity or your first isomorphism theorem or something like this, linear surjection, I should say. Um, so as sort of vector spaces, you know immediately, right, that M lower star will be the current like L1 mod the kernel of whatever this map is, right? Um, and so the next part of what I have to say will just be explaining why, in fact, this is true, even in the category of Banach spaces, right? So the point is just to go from linear isomorphism to isomorphism of Banach spaces, which is an isometric isomorphism. Isometric linear isomorphism. Okay. All right. So, well, what is this kernel that we're talking about? Well, I mean, by definition, right, it's all of those all those trace class operators for which the linear functional that I get restricted to M is zero. Sorry, I forgot to mention something. So, in my notation, just so that you can follow, when I have this psi sub A, so the of course the right vertical line in M, that's restriction onto M, but the psi sub A. So for trace class operators, I use psi to denote the linear functional that you get by taking the trace against them. And for uh, sorry, for I guess I won't go all the way back to the beginning, but for um, elements of B of H or elements of a Neumann algebra, I'll use phi. So if you see a phi subscript something, that'll be a linear functional on L1 of B of H, given by the element of a Neumann algebra. So I'll point this out. Sorry, I should have said that earlier. Anyway, so the kernel of this map is what we call this M lower perp here. This has a name in general, which is called the pre-annihilator. And we'll see later what the annihilator is. Um, and I guess at this point, I should mention before I sort of jump into all this theory here that uh, a lot of the results, in fact, I think most, if not every result in this lecture is something that holds true for general subspaces of B of H, which are sort of closed in this sigma weak topology. So you don't need the algebra structure on M to make any of these theorems true. Um, and so because of that, there's a lot of results here which are sort of in technically general Banach space theory results, which in the notes, and I agree with this pedagogical decision, are sort of just given concretely as like their specific version as relating to the von Neumann algebra. So we're not going to sort of say if X is a Banach space and blah. So I'm just going to sort of narrow my focus on the von Neumann algebra. But this pre-annihilator M lower perp is something which exists in general. And it's not necessarily defined all the time like this. I mean, it's defined in terms of duality, but I digress. So how to understand this kernel? Well, if I have an element of my von Neumann algebra and a trace class operator which belongs to the pre-annihilator, then I do this calculation. So I look at what the linear functional defined by X does to the linear functional defined by B. Well, by definition, right, I just plug it into psi sub B and I get zero because, the linear functional psi B is zero on M. So in particular, the linear functional defined by an element of the von Neumann algebra vanishes on the entire pre-annihilator. So again, this is maybe a lot of jumping back and forth, but I'm thinking of M as the dual space, right? So I'm thinking of elements of M as giving me linear functionals. And at the same time, I'm thinking of elements of trace class operators as giving linear functionals on M. So this is, again, the symmetrical sort of role that these two elements play. And so I just want to put this in here because this notation I think is somewhere in the notes, but I didn't go back far enough, I guess, to find it. So the lower perp is called the pre-annihilator, so the upper perp is called the annihilator. The annihilator of a subset of a norm vector space is the space of those linear functionals which vanish on the particular subspace or subset, if you like. And so what this argument above, this one line calculation that I did above shows you is that if I have an element of a Neumann algebra, it automatically annihilates the pre-annihilator, right? Um, so by definition, of course, what I said is that the linear functional defined by the element is zero. And so this containment is what we just showed, that M is contained in the annihilator of its pre-annihilator. And this lemma down here, the proof I'm giving here is to show that actually there's equality here. It's not just a containment. This is lemma 3.3.3 in the Gold's notes. And I just wanted to, I suppose this is one Hahn-Banach proof that I'm going to give. I will say I think maybe every lemma proposition theorem in this section uses Hahn-Banach in some way, either the Hahn-Banach separation theorem or the Hahn-Banach extension theorem. Different sides of the same coin, I guess, but because I didn't give you the Hahn-Banach proof the last time, I suppose I'll give it to you this time. So we have this containment, and now I want to say, okay, what if I have an element in the annihilator of the pre-annihilator that's not actually in M? Well, okay, so M, the Neumann algebra is sigma weakly closed, meaning to say it's a closed into sigma weak operator topology. So let's just remember how that goes. Well, if I have something which is in the closure, right, in the sigma weak operator topology, uh, then in particular, it will be in the closure in the in the weak operator topology, right? And by definition, M is a limit algebra, right? So that means that anything that's a sigma weak limit point will actually already be in M. So it's sigma weakly closed subspace of B of H. And it's not a norm topology, the sigma weak topology, but it is strong enough. It's given by sort of semi-norms. So I don't know if this has actually gone over in the last lecture, but since the sigma weak operator topology, as you might recall, is what is called a locally convex topology, right? So it's given by a certain family of semi-norms on B of H. And these topologies, while not being sort of given by an explicit norm, are still nice enough that the Hahn-Banach theorems that you would like, the Hahn-Banach separation theorem in particular, can be applied. So what we have here is an element which is not an M, right? And an element which is in M. So I guess I have two sigma weakly closed disjoint convex subsets of B of H or something like this, whatever you need for the Hahn-Banach separation theorem. By the way, this is remark 3.2.3 if you want to look. Um, so what does it mean to have these two disjoint sets? Well, the separation theorem tells you that I can find a linear functional in the correct topology, um, which will separate these two sets. So in particular, it will give you some real number t so that let's say the real part of phi of x is going to be less than t for all x in M, while um, the real part of phi of y is bigger than t. But this is a problem, right? Because um, you can find xn's in M, it's being basically just because it's a sort of a linear space, right? So you can scale elements in it as much as you like. Um, so that actually phi of xn is actually just equal to n. Um, and that means that you're going to eventually sort of extend beyond this t, right? So if you keep looking at this inequality, where real part of phi of x is less than t, well, if you plug in these xn's, or if you plug in any sequence for which the real parts go to infinity, you'll get a contradiction. So this is just sort of your classic Hahn-Banach argument, but it tells you that in fact you can identify M as the annihilator of its pre-annihilator. And again, any sigma weakly closed sort of subspace, it should work the same. Okay, like I said, anything is unclear or if I say something which is obviously wrong, I wish there was like a pelt with digital sort of rotting fruit button or something, but instead, short of that, you can just let me know and ask a question. Okay, so So we see the relevance of this pre-annihilator now, right? But in fact, we also know that what we're looking at is actually the quotient vector space of L1 mod M lower perp. And in fact, you can check, this is one of the exercises. I think it's exercise 3.3.3 in the notes. You can check that it's actually a closed subspace of L1 with the trace class operators. And so whenever you have a Banach space with a closed vector subspace, you can take the quotient and it's going to be a Banach space with the quotient norm. And I think you definitely saw this with ideals in C-star algebras, for instance, right? The quotient norm being the one given by this formula. And so again, what we're doing is just following our nose. We know that there's a linear isomorphism between this quotient and the predual. And so I'm just going to upgrade that statement into an isometric isomorphism. Okay. And so this will tell us exactly what the predual is. And I will say this later, but let me just say it now because I guess the more times I say it, the better chance that it sticks is that this theorem tells you in particular as a corollary, right? Because the left-hand side of this isomorphism is a Banach space, that the space of normal linear functionals on a von Neumann algebra is automatically, naturally, a Banach space, right? Because it's isometrically isomorphic to one, right? Which is maybe not something that is sort of obvious, right? So if I have um, like the sort of completeness argument, I mean, I guess you could try going through it, but this theorem will give you that for free. Okay, so this is a very sketchy sort of way of writing down the proof. So let's recap what happened. So we know that this map that I gave you is surjective, right? Um, in the sense of like in what sense, right? I have a normal linear functional. I extend it to something on as a normal linear functional. I extend it to something on B of H. I know that it's given as psi sub A. So that means that the linear functional that I started with was the restriction of some psi sub A, again, some trace against A, right? Okay, and the kernel is this m lower perp. So when I divide out by the kernel, I know automatically that this map that I have here, which sends the equivalence class of some trace class operator to the linear functional, is linear isomorphism. And so all that we have to prove now is that it's isometric. Okay, and I will sort of hint at that. The easy direction, which I think you should just this is just writing down like one line, just the definitions, is that the norm of this linear functional as a linear functional is bounded above by the element the equivalence class of A in this quotient space. So, of course, if you think about what is psi sub A, well, it's the trace against A, right? So you would expect something like the one norm of this A, this trace class operator A. However, the trick is, right, that you can add anything in the pre-annihilator to A, and by definition, you'll see that, of course, that psi of A plus B in this case is just going to be psi of A. So that whatever that trace is going to kill anything in the pre-annihilator. But I'll leave you to sort of check the details of that. So for the converse, or I guess the other inequality, right? So now I just need to show that these two norms are equal. I can just assume that the norm is positive on the right-hand side, because otherwise the linear functional, of course, is zero. Um, and so in particular, if the norm is positive, though, by definition of quotients, that means that A is not going to be in the pre-annihilator. Okay. All right. Well, this is sort of where the proof of the last result that I gave you is supposed to be relevant. So now I can do the same sort of argument as I did for finding that M was the annihilator of its pre-annihilator, and I'm going to apply Hahn-Banach to disjoint, whatever, closed convex, this kind of argument. So disjoint convex sets here, A and M lower perp. Now, these are I'm thinking of as subspaces of L1, right? So here I'm not using the sigma weak topology. Um, I am using the norm topology given by the trace class norm on L1. But Hahn-Banach again says that I have a linear functional on this Banach space, right? And I know that every linear functional on L1 is given by some element of B of H. And so after fiddling around a little bit with how you can sort of get different linear functionals with prescribed properties. And I think, okay, maybe this is exercise 3.3.3. Maybe the closure of M lower perp in L1 is just a sort of a byline kind of exercise. But so the point is that not only can you get a linear functional which separates A and M lower perp, you can actually choose a linear functional, which is given by some element of B of H, to be such that the norm of this element is 1, norm as an operator. Um, and that in fact, this phi sub y, which again, this is linear functional that y defines, so this is trace of a y, just the definition of this formula, is going to give you the norm of a, the one norm of a, while it's going to be 0 on m lower perp. So the separation can be sort of fine-tuned, is all I'm saying, I guess. Um, but what does this mean? Well, it means so the linear functional phi sub y being 0 on m lower perp means that y is actually that y annihilates m lower perp. And so by the previous lemma, what we get is that actually you can when you find such a linear functional that separates m lower perp from this a, well, actually you find the element of the von Neumann algebra M, right? That does this. And what does this mean? Well, if I look at the norm of psi sub A now, clearly it's going to be at least, oh, this should be a greater than or equal to, I think, the first one. And then maybe the second is an equality. Sorry. So the first step is an inequality by definition of norm, right? Y has norm 1. So this left-hand side dominates the value of psi sub A of Y. And on the other hand, I chose this psi sub A of y, I chose y rather, so that the trace of ay is the one norm of a, but that's nothing but this psi sub A of y here, actually. So I just want to say one last time, phi sub y of a is the same as psi sub A of y, right? Thinking of them as two different linear functionals, but point-wise, it's the same formula. But of course, I chose this to be equal to A1, the norm of A with respect to the trace class norm. So again, these signs are switched, which by definition is bigger than the quotient norm, right? So it gives you the other direction of this inequality. Okay. Okay, so there's your isomorphism, and that gives you the identification of the pre-dual as the space of trace class operators mod um, M perp. And if you think about it from the commutative case, right? Let's just pretend that we can do this, right? So um, this being, okay, let's just assume that this B of H, I can just swap it out for like a measure space or something, right? And M is L infinity, right? Then I'm saying that the pre-dual of L infinity would be L1 mod, whatever those L1 functions, which basically vanish, right? They give you a zero linear functional on M. Well, I mean, if you're an L integrable function, but I guess if you're a measurable function or something and you vanish sort of on your entire measure space, well, you're zero, right? So in that case, you're dividing out by is nothing. It's just zero. So this is sort of also meant to recapture this flavor of L1 is the pre-dual of L infinity. L infinity is the dual of L1. Okay, so again, I said this before, but let me just say it again. This result implies that M lower star is a Banach subspace of M upper star of the dual space of M in the induced norm. And so we have gotten halfway to our original goal, I guess. So we wanted to show that M was a dual of its pre-dual. But of course, the first step of that was actually just verifying that the pre-dual was a Banach space in the first place. Otherwise, this duality picture is not as meaningful. So we have that. So the thing that remains is to show that M is the dual of M lower star and to situate the sigma weak topology in the duality. Okay, so that's what I'll do in the remaining 20 minutes. I don't know if it'll take the entire time, but maybe with the remarks and the rambling, it'll fill it up. So remember I had this map where I had an element of a von Neumann algebra and I took it to the linear functional, which is defined by just evaluation. Um, and we saw that this map allowed us to identify M with a subset of the linear functionals on the pre-dual. And so maybe unsurprisingly, I guess now the point is just to say that in fact this map is an isometric isomorphism. So I should point this out. I don't know how closely these details were stressed so far, and I don't, and it's not, you know, it's not a crucial thing, but I just want to say, for the sake of having said it, we're thinking of M again here as a Banach space, right? So everything here is basically in the category of Banach spaces. We're not actually talking too much about algebras and such. So the isometric condition here is just the correct sort of notion of isomorphism in the category, if you like, right? Um, this was maybe hinted at by Yoon's lecture. I unfortunately missed it, but so in Neumann algebras, the correct map morphisms or maps to take are the normal ones, and I'll sort of explain a little bit more maybe at the end why that is. But for Banach spaces, which is where we're working, the correct isomorphism to think about is one as is isomorphism of Banach spaces, in particular isometric ones. Okay, so I'm going to skip the isometric part of this isomorphism proof, having just waxed poetic about it for the past few seconds. Um, Let me just say that it's basically the same kind of argument as I gave you in the previous theorem. So I'm sort of getting double use out of all of my proofs, right? You sort of mess around with the definitions. It's not so hard to see. In any case, it's in the notes. But the sort of more important part, just to understand the role that each of the guys play in this theorem, is to understand the fact that it's a linear isomorphism, which we haven't proven yet, and the role of the sigma weak topology, which I will get to on the next slide. Okay, so let's see this proof. So let's start by finding out that this map is actually a linear isomorphism. So I start with proving that it's surjective. And so what I need to do, you give me a linear functional on the pre-dual, and I want to show that I can associate to that canonically an element of the von Neumann algebra. Okay, so I understand the pre-dual now as a quotient space of L1. And so this linear functional that I have, I can identify it or view it if you want by composing with this isomorphism as a linear functional on L1 mod some closed subspace. That means that if I look at what I get by precomposing with the natural quotient map from L1 to this quotient space, I can lift this functional rho, to a linear functional on all of L1, right? By this formula here, which I have in the second line. But I know what those look like, right? So I know that functionals on L1 are given by elements of B of H. And so what I have is if I have a linear functional on the predual, I get automatically an element of B of H so that that linear functional is given by tracing against that element. Okay. So far it's pretty much the same sort of exercise of going back and forth between who is the dual and who is not that we've been doing so far. So what is this Y? Well, can we find out anything more about it? So of course I want to use this previous lemma that the annihilator of the pre-annihilator um, is just the Neumann algebra itself. So if I have something in the pre-annihilator, well, what is rho tilde of this element B? Well, it's the composition of rho with the quotient map, but the quotient map automatically annihilates everything in M lower perp. That's just its definition, right? So the equivalence class is zero. Um, and rho being a linear functional on the quotient space, it also annihilates the pre-annihilator. So if you follow out through what these formulas tell you, it will just tell you that Y annihilates a pre-annihilator as expected. So actually, what you got automatically, sort of once you mod it out by this quotient space, is an element of M, right? Um, okay. So what does this mean? Well, now that I can think of it as an element of M, this allows me actually to rewrite rho in the following form. So this is what this last line is about. Rho tilde of A, well, I know it's phi sub y of A. I know that's nothing but the trace of y against A, right? And so if I switch the roles of y and A in this equation, right, I go from phi sub y of A to psi sub A of y, which is something that I've mentioned before. This is nothing but the definition of y hat applied to psi sub A. Okay. So I just got a form for rho. I got an explicit formula for rho in terms of this element y, which is an element of M, right? And so the fact that y is an M is most prominent or is important in this very last formula in this equation, right? Because each element of M defines linear functional on the space of normal linear functionals, right? So I needed y to be an element of M for this to sort of occur. But what does that mean? Well, I had a linear functional on M lower star and I got an element of y, sorry, an element of M, which implements the linear functional, right? So modulo these identifications of the pre-dual with the quotient space and so forth, you see that actually the map described above is going to be surjective. Okay. On the other hand, well, okay, so clearly it's linear. I guess I skipped the linear part in each of these proofs, but it is linear, and this is something that you just write the formula down and you check. And so it's enough to see what happens when I land at zero under this map. So if x hat, the linear functional x hat is zero, what that just means, right, is that the trace of x against A is zero for all trace class operators A. I mean, but that's precisely what it means for x to be zero. I mean, it's not precisely what it means, but sort of taking the trace against any trace class operator and getting zero is kind of like the same argument that you might have seen where you prove that something in a Hilbert space is zero by taking the inner product against every vector and find that the inner product against every vector is zero or something like this, right? The point being that sort of the trace class operators separate points in B of H this way. And so, okay, so this tells you that this map that we've defined is actually a linear isomorphism, right? So again, there's a lot of sort of notation here which may cloud the sort of intuition, but it's essentially the same kind of routine that you do with the Gelfand thing, right? Like you think of an element of your von Neumann algebra as acting on the linear functionals on that space by point evaluation, right? And the point is just to find that every linear functional on the predual is of this form. And I guess instrumental to this is knowing actually a very concrete description of the predual, which is this quotient space. But anyway, hopefully the notation was not too cumbersome for this. short argument. So that gives me the linear isomorphism. Again, I'm skipping the isometric part. And so I guess I'm left with just talking about what is the role of the sigma weak operator topology. So again, I didn't write this in the last slide, but this is part of the same theorem, which is that the duality that I just described of Banach spaces, of course, has a weak star topology by definition of duality. This duality turns out to be the same thing as the sigma weak operator topology. And this is sort of a type checking argument. There is nothing new that you have to do. You just have to make sure that see that all the definitions that we've given point to the same thing, right? So what do I mean by this? Well, if I have a net of operators converging to some operator in the sigma weak operator topology, by definition, that's the same thing as converging against the psi sub a's, right? So the psi sub a's see the convergence. Um, but that means that you are converging sort of as seen by every linear functional phi, right? Because they're all restrictions of these psi sub a's. And that's precisely the same thing as saying is that the x hats converge weak star, right? Again, this is the pointwise convergence definition of weak star topology, right? Um, and that's pretty much it. I mean, I'm being a little bit glib, right? So maybe I can do sort of some of the right to left arrows. So starting from the very end, if xi hat converges to x hat weak star, right, that means that for each linear functional phi, which is normal, each phi in the predual, xi hat of phi converges to x hat of phi. But that's what this left-hand side means, right? That's the definition of x hat. And again, each normal linear functional is of this form, as in the line above, right? Restriction of some psi sub a. Whether or not those things annihilate M is sort of neither here nor there for this argument. This is just checking that the topologies that we've described are sort of fit into this nice chain of reasoning. Okay, so that's then that theorem. So I hope you enjoy that. It tells you precisely what we were set out to do, right? So again, we have a natural Banach space associated to a von Neumann algebra as a space of all normal linear functionals. Um, and M is naturally the dual of this Banach space. Okay. And so now let's see some of the corollaries. So this was all the theorems and argumentation. So the rest of what I have to say is just some closing remarks. And okay, I will I'll have something important I didn't write down, but I'll say it at the end. So the Banach-Aloglu theorem, as I mentioned at the beginning of the presentation, immediately gives you this: the norm unit ball of M, norm being the operator norm in this case, is weak star compact. That's what Banach-Aloglu says because there's a pre-dual space, right? So M is a dual space in particular, and that's a sigma weak topology, right? Um, so you see compactness in the sigma weak operator topology on the unit ball. And so, for instance, you know already, right, maybe, that the norm unit ball is weak operator topology compact. Well, the sigma weak and the weak topologies are the same on uniformly bounded subsets. So in particular on the unit ball, right? So you get some nice automatic compactness for von Neumann algebras. Um, and of course, as I said before, right, Banach-Aloglu is nice because you have the compactness, but it's not the same as you always think of in the metric space setting because you may not have sequences. Excuse me. Which is where I think my next remark is going. Yes. So you might often see in papers, especially on especially I've seen, I think, a lot of times for like type 3 stuff, which you haven't learned about the type decomposition yet, but remember these words when you do. You might see an assumption of von Neumann algebras that they have what is called a separable, what they say, okay, let's assume that M, this von Neumann algebra, has a separable predual. Um, why would they assume that? Well, one reason that we can see now why that is a useful assumption is because then the Banach-Arlelu theorem tells you not only that X star, the unit ball of M, is sigma weakly compact, but in fact that the sigma weak topology is metrizable on the unit ball. And so you have sequential compactness. Um, and in particular, what you can do then is you can run this argument where the separable predual assumption will give you separability in the strong operator topology, for instance, on the unit ball. Um, but once you have it on a unit ball, by taking larger scaled copies of the unit ball, you can actually extend the separability, which again requires a countable dense subset. So you can take a countable dense subset on a unit ball and then just, sort of copy and paste for after scaling for the larger um, balls, and then take the union, for instance. So this gives you sort of nice topological properties of the Neumann algebra, right? It gives you separability. It gives you sequential compactness of the unit ball, which are not for free. And I have a Stack Exchange post that I linked here, and when I shared these slides, hopefully, I think this link is supposed to be clickable. But so, for instance, you have the following sort of implications here. If I have a von Neumann algebra which acts on a separable Hilbert space, separable again for the Hilbert space means there's a countable orthonormal basis, right? So that's not the same exact thing as separable metric space, but you have a separable Hilbert space, well, then L1 as a Banach space is going to be separable in the topology sense, right? And you can see this by, looking at the density of finite rank operators or something like this in L1 and using that as sort of a countable dense subset. And so any quotient of a separable Banach space, though, is also separable. And since we had this isometric isomorphism of the predual with the quotient, um, you find that automatically you have the separable predual, right? And if the predual is separable, then you get separability in the strong operator topology, right? So, for instance, you can use the predual, or the predual, I guess, maybe gives you the sort of foundational perspective to look at certain topological properties of the Neumann algebra. And of course, as I mentioned at the beginning of the lecture, think about L infinity, think about B of H. Those spaces are not norm separable, right? Obviously, that this is sort of maybe not obviously, but it's a too strong of a topology, the norm topology for such nice things to happen. But there is natural topologies, right? There are natural topologies to give you the separability. And then the last thing that I will say, which I admit I will be a little bit, I guess, glib on the details here. So in fact, this theorem of Sakai from 71 tells you that there's another important role that the predual has to play, which is that it characterizes, let's say, abstract von Neumann algebras or W star algebras among C star algebras in the following way. If I have a C star algebra, it is isomorphic to a von Neumann algebra. It is actually what is called a W star algebra, which I'll say what that is in a second. Um, if and only if you have a predual, right? So a C star algebra, which is the dual space of some Banach space, is actually a von Neumann algebra. I do not have good examples because I tried looking for some, but there were some sort of in any case, there's no good way to sort of give you examples where the arguments are sort of self-contained. Um, but for instance, you can look this up, and it's a nice sort of deep dive into sort of functional analysis. That, for instance, the continuous functions on 0, 1, for instance, is not a dual space. And indeed, it's a C-star algebra, but it's not a von Neumann algebra, right? Um, if you think of it, let's say, as a subalgebra of B of L2 or something like this, right? But Sakai's theorem tells you, right, that it is a von Neumann algebra, a C-star algebra is a von Neumann algebra precisely when you have this predual, and that moreover, this predual is unique up to isometric isomorphism, again, in the category of Banach spaces. And then the final thing that I will say is that there is a way to define what a normal linear, okay, so let me take a step back, sorry. Start that again. The final thing that I will say is this. We define normal linear functionals by looking at what M looks like inside of B of H, right? It's those sigma weakly continuous functionals, and I restrict them to M. There is a way to define normal linear functionals, what normal means, without any concrete reference to Hilbert spaces. And it roughly goes like this. If I have a C-star algebra, let's say, and a linear functional on that C-star algebra, I can define it to be normal if the increasing net, if any increasing net, sort of, if the normal linear functional respects increasing nets of self-adjoint elements, positive elements maybe. Um, so I have a net of positive elements, and it has some supremum, right? Um, let's say I have x sub lambda, for some net, and I have a supremum x. And what I want is phi of x to be the supremum of phi of x lambda as nets again. So the point is that there's just a way to define normal, what it means to be normal without a concrete Hilbert space representation. And so then that opens the door for you to say the following. I have a C-star algebra, which again, let's say unidal, right? Which does not to be represented concretely for me to understand it, meaning to say I don't need a Hilbert space, right? I have a C-star algebra. I can define what normal linear functionals are without an explicit reference to a Hilbert space. If I can find, or if it just so happens by some miracle, I guess, that my C-star algebra is the dual space of the space of the normal linear functionals, well, then it's actually a Van Neumann algebra, right? And because there's no Hilbert space in this picture, this is sort of what we mean when we say W star algebra, right? It's something which is isomorphic to a Van Neumann algebra, but really it doesn't require the Hilbert space. It just requires a predual on which it is of which it is a dual space. Um, okay, so I think that is pretty much all that I had prepared, and it looks like I finished 2 minutes early. So I'll stop now. Thank you for the attention. And so I stop the recording now, right? And then people can ask questions if there are any. Yes.
Yep, that's correct.
Okay.